All right, so we've done our introduction to maximum likelihood estimation. I want to do one more example. And in this case, what we'll do is an example of how to estimate a linear regression using maximum likelihood estimation rather than least squares. And I'll just say again that I know that the first time or two that you see this, it's a little hard to figure out exactly what's going on and why we're doing what we're doing. So you're going to need to think through this several times and to make sure you do the reading to understand it. It's worth understanding, okay? It's worth making the effort. All right. So we're going to focus on a linear regression. So suppose there's a regression model that we're interested in estimating. Okay, and the model is yi is beta naught plus beta 1 xi plus ui. And let's, for this model, assume that assumptions 1 through 6 are fulfilled. Okay. And remember in particular that assumption 6 is that the error in this regression is distributed normally with mean 0 and variance sigma squared. Okay. If that's distributed normally with mean 0, then that implies, we talked about this once before, that yi given x, conditional on x, is distributed normally with mean beta naught plus beta 1 x variance sigma squared. Okay, if you don't remember that, go back in your notes, and I think you will find that explanation. All right, and so this variable y is distributed normally, okay? And we're interested in the fact that there's a relationship between x and y. That relationship is described by beta naught and beta 1, and we are going to want to know what the values of beta naught and beta 1 are. Because y is distributed normally, we need to make sure we understand a little bit about the normal distribution. So we'll go back and do a little bit of a statistics review. If you could see, I'm doing that when I say review, because I know that you may not have seen this before. I hope you have, and I hope it is review, but you may be seeing this for the first time. So recall that if we have a variable, and let's just call our variable, I don't want to confuse it with what's going on up here. So I'm going to call my variable z. Suppose I have, z already means something, doesn't it? We better choose a different letter. How about this? We'll call it w. Suppose that w is distributed normally with mean mu and variance sigma squared. So w is just some random variable. If w is distributed normally, then we can write the density function What is a density function? Well, when I draw a w, this thing is a density function. Okay. And the algebraic expression for it, which is what we need to write down, is this. So the density, sorry, the notation right here. The density goes by lowercase f. The density of our random variable w, which is normal, is 1 over square root 2 pi sigma squared e to the negative W minus mu squared over 2 sigma squared. Okay, that's a normal density right there. Okay. So in our case, which we're interested in, so you can say if y conditional on x is distributed normally with mean beta naught plus beta 1x, variance sigma squared, then we could say that the density of y conditional on x is 1 over 2 pi sigma squared, square root of that, e to the y minus beta naught minus beta 1 x squared over 2 sigma squared. Okay, so this is taking the variable of interest minus its mean, that's what we've got there, over 2 sigma squared. And that needs to be a negative. Okay. So we have a regression, and this describes what the distribution of the dependent variable looks like. Okay. And we can say for each I, the density looks like that. Okay. Because by assumption, the error terms are uncorrelated with one another, we know that individual observations of yi, the yi, are independent of one another. Okay. And so what that tells us is that we can think about these yi's collectively without worrying about how they relate to one another. We can just assume that each observation of y is independent of every other observation. Okay. And so we can write the joint density, the joint density of the yi's. So that's the density taking into account all values of y as follows. We can say f of y1, y2, all the way out to yn, conditional on the x's, is equal to the product as I goes from 1 to n of f of y given x. So that uppercase pi is product, and that means we can take this for observation 1 times this for observation 2 times that for observation 3, and we can take the product of all of those things to get the joint density. And so that joint density is going to be 1 over square root 2 pi sigma squared to the nth power times the product, oops, that should be uppercase, product as I goes from 1 to n of e to the y I minus beta naught minus beta 1 xi squared over 2 sigma squared and that's going to be negative. And so this thing is the joint density of all the y's, all the observations of y taken together. Okay. And what we want to do is to take this joint density, and this is what we did before with the red balls and the yellow balls, is we wrote down a joint density function. It wasn't as complicated as this one. But we wrote down a joint density function, and then we sort of rewrote it, thinking of it as a likelihood function. And that's exactly what we're going to do here. Okay. So what I'm going to do is I'm going to take the log, that is the natural log of that joint likelihood. I'm sorry, that joint density. And I'm going to think about it as a likelihood function, and in fact, a log likelihood function. So we'll say that the log of likelihood, beta sigma squared. So we're trying to find the log of the likelihood, and we're going to find the values of beta and sigma squared that maximize that likelihood. That's going to be equal to n over 2 minus times the log of 2 pi sigma squared minus 1/2 of the sum as I goes from 1 to n of yi minus beta naught minus beta 1 xi squared divided by 2 sigma squared. So we have this likelihood function, or I'm sorry, we have this density function. We wrote it this way. This is the joint density for all values of y. And what I've done is to take the log of this and to rewrite it, labeling it a likelihood function. And for this likelihood function, what I want to do is to find the values of beta and sigma squared that maximize the likelihood function. And so our task is to find beta naught, beta 1, sigma squared that maximize this log likelihood function. Okay. So how do we do that? Well, let's think about this. So first of all, what we want to do is to take the derivative of the log likelihood with respect to the betas to find the maximum likelihood estimator of beta and set that equal to 0. So let's think about this. Rather than slogging through the math, let's see if we can think our way through it. This first term doesn't have a beta in it, and so it doesn't matter. When we take the log, well, when we take the derivative, rather, we're just going to ignore this first term anyway. So for the second term, what we want to do is this. If we want to find the values that maximize the likelihood, since this thing is negative, maximizing the likelihood means finding the value of this that minimizes, that is small as possible. So we want to minimize this in order to maximize the likelihood. So to maximize likelihood, we want to identify the values of beta naught and beta 1 that minimize this thing right here. That's really the only part we care about, is that numerator, that minimize yi minus beta naught minus beta 1 xi. Okay. What is this? This is ui, and this thing squared is ui squared. Well, minimizing the squared errors, actually the sum of these squared errors, is exactly what we do in least squares estimation. And so it turns out that beta tilde, beta naught tilde, and beta 1 tilde, these are the maximum likelihood estimators of beta naught and beta 1, are exactly the same as beta hat naught and beta hat 1. So finding the maximum likelihood estimators of the betas is identical with finding the ordinary least squares estimators of the betas. And so we're done with that. We still want to find the sigma square that helps to maximize this likelihood function. And so to find that, what we're going to do is take the derivative of the log likelihood with respect to sigma squared. And that's going to turn out, taking the derivative of this with respect to sigma squared is going to give us minus n over 2 times 2 pi over 2 pi sigma squared plus 1/2 the sum of the ui squared, that is the maximum likelihood error term, over sigma to the 4th. Okay. We want to set that equal to 0. Those things offset. And so when we set those equal to 0, we get that, let's see. We get 1/2 times the sum ui squared over sigma to the 4th is equal to n over 2 sigma squared. Okay. And if we solve then for sigma squared, we will get that sigma squared equals 1 over n, times the sum of the squared residuals. And we'll call this sigma squared tilde, because that's the maximum likelihood estimator of sigma squared. Okay. And so if you remember your a little bit from 318, you know that this is a little bit weird, because in OLS, the estimator of sigma squared is, we might call it S squared, is 1 over n minus k times the sum of the squared residuals. Whereas in maximum likelihood, sigma tilde squared is 1 over n times the sum of the squared residuals. Okay. what we know is that S squared is unbiased. Okay, and it's unbiased because this n minus k, this essentially this correction for degrees of freedom, makes S squared unbiased. What does that tell us? That tells us that sigma tilde squared is a biased estimator of sigma squared. Okay, so that's interesting. It shouldn't be that surprising, because what we can say is that this is not unusual. It's not that unlikely, or that uncommon rather, for a maximum likelihood estimator to be biased. And for that reason, maximum likelihood estimators are generally considered to be appropriate only for large samples. Okay. In general, what we know about maximum likelihood estimators is this. ML estimators are, one, consistent. That is, the probability limit of an estimator, just call it theta hat, is theta. That is, if that theta hat is meant to estimate theta, that in the limit, as n grows large, theta hat will be a good estimator of theta. That's what consistency means. So consistency, remember, is a large sample property as opposed to bias, which is a small sample property. So we can't always say that maximum likelihood estimators are appropriate for small samples because they're sometimes biased, but they are generally consistent. We'll say that they are usually asymptotically efficient. And what we mean by that is that maximum likelihood estimators, ML estimator, has the smallest variance among all asymptotically normal estimators. And then the third thing we can say is that maximum likelihood estimators are asymptotically normal. So maybe those came in the wrong order, but we'll deal with it. So what does that mean? It means that as the sample size gets large, maximum likelihood estimators converge to normality. They become normal. Okay. And so among all asymptotically normal estimators, the maximum likelihood estimator has the smallest variance. And that's the story of regression using maximum likelihood estimations. So I'm going to stop there. And again, my advice would be to think through this a couple of times, read the readings, and eventually you will start to understand how this works. If you have questions now, any questions at all, let me know. I'll do my best to respond either in writing, or I can do videos responding to questions. Whatever you need, just let me know. For right now, I think I'm going to let that be what we do for this week, because I know that you still have the project to complete. You've got your introduction to maximum likelihood estimation, and the next thing we'll do is to talk about probit and logit estimation, which are specific maximum likelihood estimators. Okay, so take care of yourselves. Let me know if I can answer any questions for you, and I will be back soon. Take care. Bye-bye.